And let us say these are the two terminals of the battery. The longer one is the positive terminal, and the other one is the negative terminal. Remember, usually the negative terminal is at a potential of 0 volt, whereas the battery may be at a potential of, let us say, 1.5 volt. Okay, so this is not a battery, rather it is a cell. And as you can see, this is the positive terminal and this is the negative terminal. Okay, so this positive terminal, as I told you, is having a potential of 1.5, and the negative terminal is having a potential of 0 volt. So when I will tell you what is the voltage across this battery, I actually mean to say what is the potential difference between the positive terminal and the negative terminal. So in this way, I can say it is 1.5 volt. Okay. So always remember that potential difference is the most widely used term rather than this electric potential. But in order to understand the concept of potential difference, we need to understand what is electric potential. Okay, before that, let us have some introductory idea about this electric potential. So this concept is very useful for calculations where we are talking about the potential energy of the system. Or suppose I am having a, let us say, a positive charge somewhere in the space, and suppose I want to find what is the energy of this particle. Suppose let us say this is Q, and let us say this is Q0. Okay, so when I am interested to know what is the energy of this electric charge, then first I have to calculate the electric potential. So once I know the electric potential of this Q0, then obviously I can also find what is the if I know the potential at the point P for this Q0, then obviously I can also be able to calculate the electric potential energy at the point P. Now, electric potential is what we have already covered in the last classes. So, the concept is that your electric potential and your electric potential energy, both of them are very much related to each other. Okay, and your electric potential energy itself is related to electric field. So, in other words, we will in the future we will see that how there is a very beautiful relationship between your electric potential and the electric field. So the first thing is that if we know the electric potential Vp, then we will be able to calculate the potential energy at the point P. So once we are acquainted with this electric potential, then it is also very easy for us to calculate the electric field at the point P. Okay, so in this way, these things, since they are very much related to each other, therefore it will be widely used while solving problems. And the best thing is that two quantities are scalar over here and they are related to a vector quantity. And how they are related, that also I will tell you. Obviously, our general calculation of plus, minus, division, multiplication, all of them will not be applied. Why they will not be applied? Because here you will see how we are relating a scalar quantity to a vector quantity. So for that, we have to wait for another one or two classes, where after which we will study about the electric potential gradient. And over there, I will introduce a operator, vector operator known as your del operator. And this del operator will be responsible for converting either a vector quantity to a scalar quantity or a scalar quantity to a vector quantity. So we'll see the importance of this del operator in the last subchapter of this particular chapter number 23. Next. Next comes your electric potential. So obviously we'll go for a formal means a definition of this one. So over here it is written that electric potential is defined as the potential energy per unit charge. Very simple thing. So as we all know that your electric potential is given by the letter U, capital U. Suppose I need to find the electric potential P at a point P from the source. Okay, so I am having a source over here. So let us say this is a boundary. In this boundary, I am going to have, let us say, a source charge Q over here. Okay, and let me bring a test charge over here. Let us name it as Q0. Now, in order to find what is the potential of the charge or potential energy, sorry, if I want to evaluate the potential of the charge Q0 located at the point P, which is at a distance of R, then what I need to do is that I need to first evaluate the potential energy of the charge Q0 located at a distance of R from that of the charge Q, source charge Q. So already we have studied about this potential energy. So once we calculate this potential energy, then calculating the electric potential is very, very easy. So what we will need to do is that first we need to calculate the electric potential energy at the point P. Okay, and we have already studied that it is nothing but it is equal to the product of the source charge and the test charge divided by 4 pi epsilon 0, 4 pi epsilon 0 and the distance of separation, that is r in this case. Now, as I told you from the definition that it is defined as the electric potential energy per unit charge. So which one is the unit charge? Should I divide it by Q? No, we should divide it by Q0. That means the one where we want to find the electric potential, because this Q0 is a test charge, and I have already told you many a times that this test charge is not going to play any role in the expression. It is only there to find the parameter at that particular location, whether it is the electric field or whether it is the electric potential. For in order to calculate or find out the expression at a particular point P because of a source of electric field, then I have to bring a test charge from somewhere. So over here, as you can see, your electric potential is defined as the electric potential energy per unit charge. And please remember, like your electric field, your electric potential is always defined at a particular point in the space. So this thing is nothing but your potential energy at the point P divided by your Q0. Okay. So if we divide this expression by Q0, then we are definitely going to get an expression which is nothing but Q by 4 pi epsilon 0, 4 pi epsilon 0 R. Now, as you can very well see that this entire equation or expression of this potential at the point P is completely independent of the test charge. So, as I have already mentioned a number of times, whenever you are bringing a test charge to find the parameter at a particular location, then always remember that this test charge has no role to play in the expression. The expression is definitely going to be independent of the test charge. Only we are bringing it to test the value of the parameter, whether it is electric field or it is electric potential energy or it is going to be your, sorry, not potential energy, electric potential. Next comes your electric potential difference. Now, as I told you, rather than this electric potential, we as engineers are more concerned about the electric potential difference. Okay, and this electric potential difference can be defined as the work done from moving a charge inside an electric field from one point to the other divided by the charge. Okay, so over here just have a look at this equation. So what I told you, it is the work done from moving a charge from one point to other divided by the charge of that particular magnitude of the charge. So over here, the work done from moving a point from point A to B, we have already derived this equation, and over there we learned that it is nothing but the potential at the point A, potential energy at the point A minus the potential energy at the point B. And since we have to express it in terms of change in potential energy, therefore I have put a minus sign and I have written UB minus UA, because your change in potential energy will be defined as the final value of the potential energy minus the initial value. So if I am going to do that, then this UP minus UA is nothing but delta U. And since it is a minus sign, so minus sign is still over here. Now, I told you that this entire equation is the equation for the work done. Okay, So let me tell you pictorially. Suppose here I am having a charge Q, which is producing an electric field. Okay, fine. So this is the electric field which are moving away from this point charge in all possible directions in 3D. Okay. Now suppose there is a point A over here with a potential energy UA, and I am having another point B over here, and this B is having a potential energy of UB. Now suppose I want to move this charge Q0 in the electric field caused by this Q. Now obviously this test charge, let me move it from the point A to B. Now over here, another important thing, let me tell you that I can take any path of my choice because this is a conservative electric field. Okay, so now I can take a path straight from A to B, doesn't matter, the work done will be same as if I am going to move it in a zigzag manner like this. Okay, so whichever path I am going to undertake in order to move this test charge from the point A to the point B, doesn't matter, the work done will be same. Obviously, we have evaluated the work done. Now, we have to actually evaluate what is going to be the potential difference between the point A and B. For that, I have to calculate what is the potential at the point A, as well as I have to calculate what is the potential at the point B. Now please come to this equation. As I told you that your electric potential difference is nothing but the work done in moving a test charge from one point to the other divided by the magnitude of the test charge. So as we have already got from this above equation that your WAB is nothing but the negative of the change of potential energy. And if we divide this WAB by Q0, then obviously on this right hand side, we have to also divide it by Q0. Now just look at this equation. I have just mentioned that this minus del U is equal to minus of UB minus UA. So divided by Q0. Now if you can see, this is a term which you are already familiar with. This term is nothing but VB, that is the potential at the point B. Similarly, this particular terminal is nothing but the potential at the point A. Okay, so these two things, if we will put it over here, then this is going to be minus of VB minus VA. So if I take this minus side inside, it is going to be VA minus VB. And in total, this is nothing but the potential difference VAB. Now remember VAB, when AB is written in the subscript close to each other, it defines or it represents the electric potential difference. Whereas VA and VB indicates the potential at point A and B respectively. So please don't get confused with this. Very simple thing. Potential at A minus potential at B is equal to the potential difference VAB. I hope everybody have understood. Since I can't hear you, please write a yes if you have understood. If you have not understood, please write no. I'll explain once again. Please write down in the chat box if you have understood it. If you have not understood, if anybody of you has not understood, please write no. Okay. I hope everybody have understood. Yes. Gurman. Gurman, can you please tell me why I just can't hear your voices? Do you have any idea? Because without hearing you people, it's quite difficult to change the screen very frequently. Is there anything wrong in the settings? I haven't changed any
No,
setting.
sir. No, sir. Nothing is wrong.
My goodness, I
No,
can
sir,
hear your
everything
voice.
is okay.
So, please tell me once again. Please speak out.
Sir, understood, sir. No problem.
No problem. Thank you, Deepak. Actually, I'm very happy that I could listen to your voice. Okay, thank you. So let us move on.
Welcome, sir.
Okay. So till now we have covered what is this electric potential difference. Now let us further move. So now, yes, it's okay. We have learned what is this electric potential. But let us, as an engineering student, let us practically try to understand what is actually this electric potential difference. So over here, one battery is given. This is, I have just copied it down from the book. But let me explain you what is actually happening inside that battery cell. Okay. So please be attentive. Let me tell you what is actually, what do we mean by this electric potential difference. Okay. Now, please look over here. Here I am having the positive terminal, and over here I am having your negative terminal. Well and good. Now, obviously, if I am having a source, I also need a load, okay, because the need of the source is only to provide energy to the load to do some work. So let us say this is the load. And when I will connect it, so what is going to happen? Now, obviously, the electrons will start moving, okay? The electrons will start moving in this path, right? It will start moving from the negative terminal of the electrode, and it will pass through this resistance or the load, and it will enter into the positive terminal. Okay. Now obviously this is not the conventional direction of current, it is actually the actual direction of current, because in plus 2 you must have studied that in actually the direction of the electrons is actually from the negative terminal to the positive terminal. But since we have learned that your charge flows from the positive terminal to our higher potential to the lower potential, so rather we represent it by means of the conventional direction of current, that is from positive to negative. But now, in order to understand the concept of potential difference, we have to actually take the actual direction of the flow of electrons. Now, just have a look. So obviously, when a lot of electrons are accumulated on the side of this negative terminal, so naturally this negative terminal is flooded with negative charges. Okay, and the positive terminal on the positive anode is flooded with positive charges. Okay, now obviously inside this cell there is some chemicals which are interacting with each other, or there is a chemical reaction which is actually going to produce, or rather I will say going to separate the positive charges from the negative charges. And remember, the chemical reaction is the one which is actually doing the work of conversion of this chemical energy to the electrical energy. So inside the battery cell, there is some chemical reaction which is actually forcing the positive charges to accumulate on one side and all the negative charges to accumulate on the other side. Now, let me tell you in a very clear manner that obviously the positive charges are massive in nature, they cannot move. But the fact is that all the electrons which are present over here, over here, over here, they will be dragged towards the negative terminal. Okay, I hope everybody is understanding. Is it clear to you all? Is it clear? Yes or no?
Yes, sir.
Okay, so fine. So positive and negative charges are evenly spread along the body of this cell. But because of the chemical reaction is actually producing some force, or it is producing some energy, which is actually responsible for separating the negative charges from the positive charges. So what it does, it pushes all the negative electrons to one side, and therefore the other side becomes flooded with positive charges. Now obviously when negative charges are dumped or pushed to one side, like charges repel, this thing we have already studied. So naturally what it is going to do, the moment I will connect it through a closed path, these electrons which are repelling each other will try to move in this path, and it will try to move in this direction, and will try to come and dump themselves on the positive side. Again, because of the continuous effort of the chemical reaction, again this electron will be pulled and it will be dumped on this side. So this is the process that is continuously taking place till the chemical reaction is there. Once the chemical reaction has stopped, then the battery is dead and all the positive and negative charges, they will again combine with each other. Now, please look what is
Sir,
actually, yes?
this process can be done by the opposite side also.
Yes, no problem. Your positive charge can move.
Only
Yes, of course. The positive charges can, when it will start moving from the positive to the negative terminal, again it is going to be known as current. But the problem is positive charges are massive in nature. That is the reason why they are immobile. Whereas these electrons are quite light in weight and they are placed in the outer cell of your atom, and therefore they are easily available for transportation. Got it?
yes, sir.
Are you okay? Got it?
Yes, sir. Got it.
Okay, fine. Fine. Now let us move on. So, what is actually happening? Now, as I told you, when all the positive charges are on one side and negative charges are on the other side, then obviously there is a creation of an electric field. And maybe this electric field is going to be somewhat uniform because all the electric field directions or the field lines are going to be directed straight from the positive to the negative terminals. Okay, so well and good. Now, what is this electric potential? Let us try to see. Now, once I have separated the positive and negative charges, then obviously at the positive terminal, let us say this positive terminal is point A and this negative terminal is point B. Now, what is going to happen? Now, all the positive terminals are pushed to the side A, and therefore they are separated from the electrons, and therefore they are going to get or gain some energy, that is UA. Similarly, all the electrons are pushed and dumped on the side B, and therefore, since they are separated from the positive charges, they are definitely going to gain some energy, that is UB. And always these two inside the cell, they always try to mix up and neutralize their charge. But the problem is that the chemical reaction is forcing them to remain apart from each other. Therefore, there is always a presence of electric field inside the cell. Now, when you are going to connect a load to this type of source, then it is getting another path to move on. So, what is going to happen? These electrons, which are less massive, they will start moving from this point B towards this point A to neutralize because they always want to have minimum energy state. That is the universal law. Now, what is this potential energy? Now, this potential energy, as you can see, just imagine that one of the electrons has mixed up and it has neutralized. Suppose this electron is dumped over here, and in the circle, you can see positive and negative charges are there. Now, what is going to happen? Since the chemical reaction is forcing them to separate, therefore, this electron will be forced to move against this electric field because electric inside the electric field the electrons move in a direction opposite to the electric field, but here because of the chemical reaction some force is forcing this negative electron to move against the electric field and get itself dumped over here. That means some work is being done on this particular electron, and that is known as electric potential. And if I am going to consider that, then obviously all those electrons will move from point A to B. So naturally, there will be a potential difference between the point A and B. So that is what I have written in bold letters. Please go through it. In other words, your VAB is the potential of A with respect to B is nothing but equal to the work that must be done in order to move a unit charge, not slowly, maybe fast, doesn't matter, but in the book it is written slowly, forget about it, to move a unit charge from B to A against the electric field. Please note it, it is always against the electric field. That means when I am going to move a charge from one point to the other forcibly, then there is some work done. Okay, if there is some work done, then there is some potential energy, and if I divide that potential energy by the magnitude of the charge which is actually moving, then I am going to get the electric potential. And obviously in between 2 points there will definitely exist a potential difference. And remember, in Kirchhoff's law in your plus 2 you have studied that if there is a potential difference and you connect it across a load, then it is going to power up that load. Okay, so the unit of this potential energy, sorry, a potential difference is your volt. So that is the thing that we always encounter in our daily life. So inside your home you will see a socket like this, which is consisting of a bigger diameter pin followed by two small diameter pin. The one on the right is the fetch point, the other on this side is the neutral, and the one on the top with a greater diameter is the ground. Forget about the ground, it is reserved for only electrical students. Okay, so now let us talk about this thing, P and A. Now obviously at this point it is at a potential difference of 230 volt, whereas this ground or this neutral, both of them are at a potential difference of 0 volt. So this neutral and this ground, both of them should be ideally at 0 volt. But sometimes it doesn't happen. So if I am going to connect some load between this P and N, then obviously your electrons will start moving because there is a potential difference between the point P and N. And when there is a potential difference, we call it as volt. So when a voltage is applied across a load, a current starts flowing. So in this case, when I'm going to connect a load between the point A with a potential of 230 volt and the point N with a potential of 0, then obviously in between the point P and N, I am having a potential difference of 230 volt. So when I am going to connect a load to a 230 volt source, then obviously it is going to give energy to the load to do some work. So this is the concept of potential and potential difference. And the underneath or the underlying work that is taking place inside any source, whether it is a battery or it is a cell or whether it is a generator or whether it is an alternator or whether it is a solar cell, doesn't matter. The principles are all the same. That is why they are categorized as energy sources, which I have told you in the lab in the demo class. Is there any doubt from anybody? Please clarify it. Yes? Anyone with any sort of doubt, please be frank. Tell me, I'll clear it. Shall I move ahead? Tell me yes or no. Yes?
Yes, sir.
Okay, I hope so. Nobody is having any sort of doubt. That's a great thing. So let us now move on further. Please be online. Please be online for only 1 minute. Okay, so let us now move on. Okay, electric potential due to a single point charge. Now we'll talk about the electric potential due to a single point charge. Already I have explained you, but let us now formally try to explain it. Now, we know that your electric potential Vp, that means the potential at the point P, is equal to the potential energy at the point P divided by Q0. Okay. Now, what is this Q0? It is a test charge. Remember, it is not going to play any role in the calculation or in the expression of potential at a point P. So just have a look. So as I told you, electric potential is given by the potential energy at the point P by Q0. That is the test charge we have brought. So just have a look at this diagram. So over here you can see there is a source. Okay, let that source be Q. Now this source is producing an electric field. Now I want to find the electric potential at the point P. Now I cannot simply find out the electric potential at the point P. For that, I have to bring a test charge Q0 from somewhere. So now what I will do, I will bring this test charge and place it at this point P. So when I will place it, now I will be able to calculate the electric potential energy. So what will be the electric potential energy? It is given by this term. We have already covered this one. U is equal to U, rather I will say UP. UP is equal to QQ0 by 4 pi epsilon 0 R. So what is R? R is nothing but the distance between these 2 points. So this is your distance of separation R. No need of writing it in vector because all of them are scalar quantities. So if this is the case, then as per our definition, the potential due to a point charge at the point P is equal to this potential energy at the point P divided by Q0. So ultimately, I'm going to get this expression. So the electric potential at the point P can be written as Vp is equal to Q by 4 pi epsilon 0 R. And the best thing is that this, as I told you, as we have already experienced, that this test charge is not going to play any role. Or rather, I will say that your electric potential is completely independent of the test charge. That means the purpose of the test charge is only to find the electric potential. But in order to find that, I have to bring a test charge to do it. Okay. Next, obviously, in a space, I may not have a single point charge. I may have a collection of point charges. Okay. If that is the case, then how we are going to find the electric potential at a point P? Okay, so let us say there are multiple number of point charges like Q1, Q2, and let us say Qn. Like this, we have having a number of point charges, and I want to evaluate what is the electric field at the point P. Then obviously the equation that is going to help us must be having a summation sign. So if we will look at this equation, then very easily we can guess that it is definitely going to be 1 by 4 pi epsilon 0 summation starting from 1 to n qi by ry. That means the distance between this q1 and this point P is equal to r1. Similarly, between q2 and this is r2. Similarly, between this Qn and this P is equal to Rn. So in this way, I have to find the magnitude of each of these charges as well as if I know the distance of separation between these point charges and the point of calculation, then obviously everything turns out to be damn easy. Okay. So this is the equation. So this is the potential due to a collection of point charges. Okay. Now, another interesting thing, let us see from this diagram. Now, over here, I'm having a single point charge, okay, or maybe a charged body, doesn't matter. Now, as you can see, your Vp is inversely proportional to R. That means the closer I will move towards the positive charge, the potential is going to increase. Similarly, if I am going to move out, the potential is definitely going to decrease. And remember, it is only in case of positive charge. The opposite is going to happen for negative charge. So if I am going to move towards the positive charge, then obviously towards the negative charge, my potential is definitely going to decrease. Whereas if I move away from the negative charge, my potential starts increasing. Okay, or the value of this potential is going to increase. That means if I am having a point P at this point P and another one Q over here, naturally P is going to have more potential than that of your Q. That means your Vp is going to be more than that of your Vq in case of positive charge. And if it is a negative one, then the opposite is going to happen. That means your Vp will be less than that of your Vq in case of negative point charge or negatively charged body. Now let us move on to electric potential due to a charged conducting sphere. Okay, I have already discussed, we have already learned, we know the difference between a charged conducting sphere and an insulated conducting sphere. So what is a charged, sorry, insulated solid sphere? So what is a charged conducting sphere? Yes, anybody? Anybody with any idea? What's the difference? Maybe in the exam you will get a question, what is the difference between a charged conducting sphere and an insulated solid sphere? Then you have to answer it. Yes, tell me.
So
Charges will
insulated
accumulate
conducting sphere
on
is
the
not
edges.
grounded,
Okay,
or
okay.
a
There are
charged
two
conducting
answers
sphere.
simultaneously. So please tell me one by one.
The charges will accumulate to the outer surface of the conductive sphere, the
Okay,
sphere which is conductive, and in case of insulated, it won't happen. It will,
okay.
it may be uniformly distributed.
Yes, yes, that's the case. Okay. That means just see, if I am now, let me tell you another important thing. Maybe I haven't told you people. Suppose let us say I am having a sphere like this. Okay. And let us say it is a insulated sphere, right? So if I am having an insulated sphere, how actually it is going to look like? Suppose I will insulate it on the top like this. I will insulate it. Then remember all the positive charges will be on the inner periphery. Okay. Now the same conducting sphere, the blue one is now the conducting sphere, and on over it I will give an insulation, oh sorry, inside it I will give an insulation. Okay, then in this case all the positive charges will be on the outer periphery. Okay, so this is the meaning of conducting sphere, and the difference is if we are having a conducting sphere only, then on the side which one is a conductor the charges will accumulate, whereas on the inside it is going to be zero. Sometimes you may see that there will be an insulation and this insulation will be grounded. Sometimes we used to write, give questions like this. So if it is same, because on this side the insulation is grounded, that means no charge is going to get deposited on it because all the charges will be directed to the ground because the ground is at zero potential. Okay. Similarly, the blue one over here is the conducting one. So you will bring a charged object and you will just touch it, then all the positive charges will uniformly distribute only in the outer periphery. In this case, the outer one is going to be grounded. Okay. And if the inner one is the conductor, you will bring and somehow you will touch the inner one, then all the positive charges will accumulate on the inner side. And usually this concept will arise in case of hollow sphere or hollow volume. Okay. Next, the solid one. In case of solid one, usually we say that if I am having a solid sphere like this and it is insulated, insulated means always remember it will be insulated only on the outer side. Because if it is a solid one, then obviously the same conducting material is inside it. Okay, on the outer periphery, I have the insulator. So this insulator is grounded. So this is known as an isolated insulated solid conductor. So your positive charges are going to distribute themselves throughout the entire volume of the conductor. God, I hope you people have understood this. Or is there any doubt? Okay, fine. So let us now evaluate the electric potential. So if I am having a volume, so let us try to find what is the electric potential at three different locations. Okay, so one on the outer side, the other on the surface of the sphere, and the last one inside the sphere. Okay, now here you can see everything is very self-explanatory. So outside the conductor, when your small r is greater than capital R. Okay, don't worry, we are not going to apply Gauss law. Now, just have a look. The field outside the sphere is the same as if, please remember, as if the sphere is replaced by a point charge. So, if I am having a sphere like this and I want to find the electric potential at the point P, then in this case, let us say the distance between the center and this point P is equal to small r. So in this case, the first thing that I will do is that I'll replace this entire sphere by means of a dot like this or a point charge. Why? Because here the volume, the surface area, they have nothing to play at all. They are not going to play any role. But when we are calculating electric field, over there we are applying Gauss law, and for that Gauss law, we require the expression or we require the knowledge about the volume and the Gaussian surface. Okay, for that we were calculating every all those stuff we are doing. But now in this case, there is no need of calculating any surface area or Gaussian area, closed surface area or volume. Nothing we require. So very safely, I can say this entire sphere of, let us say, Q dash charge is going to be replaced by means of a point charge carrying a charge Q dash. And from here, I have to find the point P located at a distance of R from this point charge. And I will just use the formula for point charge to evaluate the electric field. So obviously for a point charge, it is nothing but Q by 4 pi epsilon 0 R. So exactly the same formula or expression is going to be applicable in this case. Because here what we have done is we have replaced the entire volume by means of a point charge located at the center of that conducting sphere. Clear? Is it clear to you all? Or is it clear or not? Or once again I have to tell. No response?
Clear, sir.
Okay, fine. Just respond to me because otherwise I will keep on moving without acknowledging whether you have people have understood or not. Okay. So two-way interaction is damn necessary. Okay. Now let us now evaluate the electric field on the surface. Very simple. In the same way as we have done previously. In this case, we'll replace the small r by means of a capital R. So the equation turns out to be this much. Okay. Now, inside the sphere, okay, I have done some mistake. Okay, no. Inside the sphere, r is less than r. Small r is less than capital R. Now we are interested to find it inside. Okay. Now, in this case, the electric field is zero inside it because you all know that in case of positive charges, all the electric fields are directed away. Okay, they are directed away, not inwards. So inside the electric field is zero. Okay. So if this is the case, now in order to get the expression, we will approach in a little bit different manner. Okay. Here we cannot consider the sphere to be a point. Why? Because the electric field is moving away. So in the previous case, when we were calculating the electric field, because of this conducting sphere somewhere outside, over there we can consider it to be a point charge. Okay, because the calculation is done from the center of the sphere. Now the same thing cannot be applied to a point inside the sphere. Why? Because in this case your electric field is all going to be radiated away like this, and therefore no field is going to be present inside it. Now, if there is no field present inside it, okay, and let us say I will place a charge Q0, okay, then one will be tempted to know or say that obviously this Q0 is equal to is not going to sense any electric field, and therefore the potential is going to be zero. Is it? No, it is not like that. How we are going to do? Now just look over here. Hence, okay, just have a look over here. Inside the sphere, E vector is zero everywhere inside. Okay, hence no work is done on the test charge that moves between any points inside the sphere. This means that the potential is same at every point inside the sphere and is equal to the value at the surface. Now, a little bit confusion may arise in your mind. Let me clarify that thing. Now, as I told you that inside this there is no electric field because all the electric fields are directed from the surface outwards like this. That means inside there is no electric field. Okay. If this is the case, then how we are going to evaluate this one? Now, if this is a point P and there is a point a charge over here, okay, this point charge, okay, then obviously this is at the surface and the electric field from this point is same as that over here because obviously inside it there is no electric field, but the potential over here and the potential over here both are going to be the same. Okay, because when moving it from this point to this point following any path, it results in zero work. So the potential difference is zero, but the potential is not zero. Why? Because it is getting affected by this surface, only one point at this surface. Okay, it doesn't matter whether it is over here, here, or where, anywhere. Why? Because these points are not going to get added up over here. Why? Because this is not a vector quantity. If it would have been a vector quantity, then it would have been zero because all of them are dimensionally or they are going because of the symmetry, they are going to cancel out the effect. But in this case, it is not going to be like that. So these points are all added together is going to give the potential at the point P. And what is the total potential on the surface? It is nothing but the Vpq by 4 pi epsilon 0 r. Is there any doubt? Then tell me, ask me. If there is any sort of doubt, please ask me. Because here the confusion usually arises. Inside, there is no electric field, but the electric potential will not be equal to zero. It is equal to that at the surface. Okay? Now the same thing has been drawn over here in this diagram and usually this question comes. The question usually the statement is like this. The electric potential at, the electric field at a particular point in space is zero. Is it true that every time the electric potential will also be zero? Yes or no? Can anybody answer it? The question is very simple. The electric field at a particular point in space is zero. Is it true that the potential at that point in space is always going to be zero? Yes or no?
No, sir.
Yes.
No. Whoever has told yes, that is wrong. No, it may be zero, it may not be zero. Okay? It may be zero, it may not be zero. Okay? Yes, it is going to remain constant. So starting from this point in the space, sorry, in the periphery, whatever be the potential, it will remain everywhere inside it also, it is going to remain the same. Now, if you can't remember this, I am going to give you a very beautiful example. Okay, let me tell you. Now, let us say this is the surface of the earth, and everyone from you know one concept that in electrical wiring of your house, we have something known as earthing or grounding. Okay. Now, every house is going to have some earthing material, or there must be an earthing pit where you dig a pipe made out of galvanized iron into the earth. Okay, 6 feet into the earth. Okay. Now, why is it so? Because we all know that the earth is at zero potential. Okay, so whether you are putting it in, suppose somebody is, or example, your electrical department in ITR is having an earthing pipe in E block. Whereas computer science department in C block is having its earthing pipe in C block. Okay, but still then everywhere the value is equal to 0. Now the earth is one. Whether you put it over here or over here doesn't matter. Whether you have an earthing at North Pole, one at the equator, the other one at the South Pole, doesn't matter. The earth is always at zero potential because inside the earth's surface the electric field is same as that of the surface of the earth, and the surface of the earth is at zero potential. Got it? Is there any doubt? Okay. Another important thing, I will tell you very interesting thing. When we talk about this earth, it is nothing but an equipotential surface, which will be taught to you after 2 or 3 classes. Okay, after one class, we will talk about this equipotential surface. Okay. So I hope everybody have understood. Next, let us move on to electric potential due to a uniformly charged ring. Okay, these two things are very common every time, whether it is electric field or it is electric potential. We always try to find for different configurations of charge. And one of our favorite configuration is sphere. The other one is a ring, a uniformly charged ring. Okay, so let us now evaluate for a uniformly charged ring. So the question is very simple. We are supposed to evaluate the electric potential at a point P, let us say, and this point P is located at a distance of small x from the center of the ring. Okay. Now this x, y, z I have given as the coordinate axes. Okay. Next, let us calculate the electric potential at the point P located at a distance of x from the center of the ring. And obviously, since it is a ring, it is definitely going to have a radius, and that radius is equal to a, small a. That's it. Now, this entire ring is carrying a charge of Q. That means it is uniformly distributed along the periphery or along the perimeter of this ring. Now, as I told you, since this is a continuously charged body, we have to make use of integration to integrate and to differentiation to find the electric potential due to a very small portion of this ring. Okay, so let us say this small portion is equal to dy or dl, doesn't matter. Now, obviously, this DL is going to produce an electric field, sorry, not electric field, it is going to produce an electric potential at the point P. Now, when I am talking about DL, I have told you some interesting thing. So, this DL can be considered as, yes, can anybody tell me? Can anybody tell me what I will consider this DL? This DL is nothing but what? Many times I have told you while solving these types of problem, DL, DS, DV, I can consider them as, yes, nobody have remembered it. Yes, tell me.
Yeah.
Yes,
D very small,
we'll consider it as a DL is
very
infinitesimally
Small
small.
portion.
small
Small?
length.
Okay,
Portion
DL is a
of
very small
ring.
length. No, I haven't told you like this. I have told you very precisely one important thing. No, whatever I am telling you, and since you all are in first year, so this is your fundamental science. So these things you have to remember. Okay. Okay, let me repeat it. Whenever I told you that I'll be dealing with a very small length like DL, a very small area like DS, or a very small volume like DV, all of them will be considered as a point charge. Haven't I told you? Yes, of course I have told you. So all of them can be considered as simply a point charge because this DL is infinitesimally small length, which is nothing but it is just like a dot, like a point. Similarly, a very small area that is nothing but a dot or a point charge. Similarly, a very, very small volume, that is nothing but a point or a point charge. Okay, so in this case, we will take this small portion as a very small length, and therefore we can consider it to be a point charge. So what is the formula for point charge? So a point charge is Q. Because of a point charge, the potential at the point P at a distance of R is given by Q by 4 pi epsilon 0 R. Yes or no? We have just studied it right before 10 minutes. Okay. Now, since we are going to integrate it, now since it is dl, we can say your q is nothing but lambda into l, lambda into l. So if I am having dl, then obviously it is going to be dq. So let me replace this q by means of a dq, and let me integrate it from 0 to q. Doesn't matter, because the entire charge is uniformly distributed. So the total charge of on this ring is equal to 0 to q, because I have replaced it with a dq. If I would have replaced with a dl, then I would have got something else. Even that is also, that way also you can solve it. So no need of going for another extra step. So simply let us write it as dq. Okay. Now here r needs to be expressed differently. How? Because here in this problem only two things are given. One is the distance from the center, the other one is the radius. That means I have to express this r in terms of x and a. So obviously r can be expressed as x square plus a square, Pythagoras theorem. So r is equal to x square plus a square whole root of r. Now we replace this r by means of this term, and ultimately you are going to get this as the expression for the electric potential at the point P located at a distance of x from the center of the ring of radius A. Okay. Now, there are two important notes that are associated. One, at the center of the ring, x is equal to 0. Obviously, x is equal to 0. So, if that is the case, then what will be the expression for Vp? Obviously, remove that x. So, I am going to get q by 4 pi epsilon 0 into a. Next, if that x is at a very far distance from that of this one, such that your x is many times greater than or much greater than that of your a. So since these are square terms, obviously I can neglect this a square in comparison to your x square. So ultimately what I am going to get is Vp is equal to q by 4 pi epsilon 0 x. Okay. So I hope you people have understood. Now the time is up. If you people have a little bit doubt, tomorrow I will repeat it once again and we'll move further. And we'll definitely try to complete the chapter tomorrow. We'll try to complete it. Okay. So please be online. I'll just take a print screen. Then you people can leave. Now you all can leave. Okay. You may be having class. Let me leave. Okay. Bye.